Hello everyone, my name is Viraj and today we'll be looking at the 13th problem from the CP-31 sheet by TLE Eliminators under the 900 rated questions. Let's go. So moved on to my CP-31 sheet over here, ticked off 900 rated parameter and 13th problem, NIT Destroys the Universe. Let's read this. For a collection of integers s, define max of s as the smallest non-negative integer that does not appear in s. Alright, now NIT the cleaver decides to destroy the universe. He's not as powerful, so he has to snap his fingers several times. The universe can be represented as a one indexed array A of length n. So when NIT snaps his fingers, he does the following operation on the array. So now we read the operation. He selects positive integers L and R such that 1 is less than equal to L is less than equal to R is less than equal to N, and let W equals to max of these numbers, that is from AL to AR, and then you will set all the values from all the values AI from L I belonging to L and R to that W value, and then we will say the universe is destroyed if I feel that every value from 1 to n AI equals to 0 is holding. And you have to find the minimum number of times NIT needs to snap his fingers to destroy the universe. That is, find the minimum number of operations NIT needs to perform to make all the elements in the array equal to 0. Alright, let's read this problem, generalize this problem, and understand what are they saying. So they are defining an array of n size, of course. So I'll call this array A, and the numbers are A1, then you have A2, A3, A4, so on till AN. These are the numbers. Now they have defined something to be very special. It's a sort of a good concept that is called max. Alright, what are they saying is a collection of integers s will have max of s as the smallest non-negative integer that does not appear in that collection. What does it mean? I'll give you a small example. Let's say I have some numbers, a collection is there, some numbers, let's say 5, 2, 1, and let's say 3. Now in this, if I ask you, what's the smallest non-negative integer? Non-negative integer means anything that's greater than equal to 0, or basically if we know in maths concept, this is called whole numbers. So anything greater than equal to 0, tell me which is that smallest integer you think doesn't exist in this. Let's start off with the very start. You obviously want integers greater than equal to 0. So you begin with 0. Do you ask, in this set, do I find 0? No. Is 0 a non-negative integer? Yes. Is it occurring in the set? No. So I can simply say that the max of s becomes equal to 0. Now, had I removed 1 from here and I made it 0, then the max of 5203 would be 0 is there. What's the next integer greater than 0? We are looking at 1. Now, is 1 present? No. So I know that now the max of s would have changed to 1. Let's say 1 was also there. Then the max would have become 2. Let's say 2 was also there, then the max would have obviously become 3. And let's say 3 was also there in this case, then you can say 0, 1, 2, 3 all are present. Then the next integer that's not present, it's 4. So I know max of this has become 4. So this is a very small concept that is used in this problem that is called max of some numbers. Pause this video, try to understand this concept by taking some case on your own and understand this whole concept of taking small integers collections and finding the minimum integer in that which you think is not present, that is greater than equal to 0, or non-negative, that is actually the max. Once this idea is clear, now we can understand the problem. So coming back to our main case, we have an array of n size a1 to n numbers. Now I have been given an operation. Okay, what can this operation do typically? This operation can do a very simple thing. I will say that in this operation, I will select some L and R, right? Some L and R, which would denote indexes. So L less than equal to R, of course, and L and R both are in this index 1 to n range. When I select L and R, it's basically selecting some segment of the array, some range of the array, and then I will find the max of all the numbers in that range. So let's say I select L equals to 2, and let's say I select R equals to 4. So I'll find the max of A2 to A4. That is this collection. I'll treat this as S, and I will say, okay, this is, or this could have been my S collection. Find the max of A2, A3, A4 as a collection. Let's say the max of these numbers turn out to be, let's say, assuming they turn out to be W. That's what the integer they are saying. So I'll say the max became W. So I will replace every number in this segment as W. So now modification has been done and array is manipulated. Original array is not retained. You have a new array where you start off with. Now you do one more operation, keep on doing it. And the question is, what's the target? Where do we stop? Of course, we stop where we feel all the numbers have finally turned out to be 0. That is, I want to make my array to look something like this eventually. 0, 0, 0, 0, 0, 0, so on, n zeros. If I'm able to do this, I know I can stop. And the question is saying, do this, make your array go to all zeros and do this in the minimum number of operations possible. So this power that is given to you, minimum operations possible. This power that is given to you of taking an L2R range, finding the max, replacing all the numbers in that range with that max number, do this the least amount of number of times and finally convert your array to be 0. Now whatever this value turns out to be, whatever this number turns out to be, I'll call this as answer, and this is what I want to return. So this is the whole problem. Let us see some sample case and understand this very clearly. What do they mean by this? Let's say I'll take a small example over here. 0, 1, 2, 3, 4. So you have 5 numbers, 0, 1, 2, 3 and 4. Now in this, very, very simple. Can I pick up the numbers in this range? Yes, I can. And if I ask you what's the max of these numbers, 1, 2, 3, 4, of course, the max of these numbers are 0. Pause the video, give it 2 minutes thought, you will understand the max is 0. Of course, because 0 is the only integer, that's the smallest non-negative integer, which is not occurring in this collection 1, 2, 3, 4. That means 0 can be found, and very simple. How about this? The first number, of course, remains 0 because that's not the part of my collection, but these 4 numbers turn out to be 0. And doing this, have I finally received the full array to be all zeros? Yes. And how many operations did I do? Only one operation. So can I say 1 is my answer? Yes, 1 is my answer. And if I go back in the case, yes, 1 of course is the answer in this question. So this is the whole problem. I hope the sample cases are clear. Let's do something. Now, before we discuss the idea of the problem, let's try to first understand what are we expecting in terms of time complexity in this problem. Alright, so a very simple discussion. We know, like I'll rub all this out. We all know that in 1 second, I am allowed 10 raised to 8 operations. This is by fact. But in this problem, I have been allowed 2 seconds to run for every test. So if I talk about one test, it's basically telling me that, okay, run 10 power 8 or to be specific, 2 into 10 power 8 number of operations in one test. Because this is 2 seconds, so of course 1 second for 10 raised to 8, 2 is 2 into 10 raised to 8. Now, in every test, there are some test cases that is denoted by this variable t, which is in 10 power 4 order. So technically, I should calculate the number of operations per test case. But there's a catch. It's written over here that sum of n, that is this size of the array, in all test cases, overall test cases, as in the summation, does not exceed 10 raised to 5. Which means that if I have, let's say, the highest number of cases, let's say I have, in this case, I have one test file can have 10 power 4 cases. So let's say I have 10 power 4 test cases with me. In every of this test case, let's say n1, n2, n3, so on, n values, when I sum everything up, I still remain less than 10 raised to 5 order. Or to be specific, this is 2 into 10 raised to 5 order, 2 into 10 raised to 5 order. Now what does that mean? That means that I am not looking for number of operations for every test case. Rather, I am looking for number of operations in every test, because I am looking at a summation n total. This can be taken as a bigger n, which is in orders of 2 into 10 raised to 5. And this is the variable for which I can reference out my time complexity. Which means that now if n is given approximately in 2 into 10 raised to 5 order, in comparison with 2 into 10 raised to 8 operations in every test, if I create a solution that looks like O of n, it's going to work. Maybe like O of n log base 2n, it's also going to work because it's less than, if you plug n as 2 into 10 raised to 5, you are still less than 2 into 10 raised to 8 order. You will still be good to go if you create a solution that looks like O of square root of n. This would be like barely passing the cases, not very ideal to create, but eventually if you do a very acute mathematics, you will find that the number of operations is still less. So it might have a chance that this also passes. But if you actually, like, a better approximation would be that if I start getting solutions in O of n square order, I will fail over it. So this is bad for me. This is sort of an upper bound. I cannot create this, but anything this like this and below this is good to go. So below this means if I go even down and I'm able to create something like a constant time complexity solution, that's all good to go. Alright, so this is the expected time complexity discussion, and this is very important because now I know that I'm looking for solutions ideally in O of n order. I'm not looking for solution that goes in brute or like n square order. That would not work, and hence now I can think some ideas in this problem. Alright, great. So now let us finally try to understand this problem. Let's see what idea do we have. So ideally this problem is a very sort of a test case based problem. Alright, the argument is very simple. Let's try to pitch the argument first. Answer is at most 2. This is the whole argument. What does it mean? I mean to say that answer is either 0 or 1 or 2. Answer is not anything beside these 3 values. Now this is a very strong argument, and to present this, of course there are some if and else checks and if and else case making which we have to understand. So let's try to picturize small observations very simply. A very simple observation will come to the mind is I can look at the sample case and see that 0 is an answer. So even if I don't pitch you that answers are only 3 possible cases of 0, 1, 2, you can understand that 0 being an answer would make sense. I can start off with my cases being the very base case. When is the answer 0? Of course the answer is 0 when you know every number is already 0. So I don't need to even give you a very lengthy explanation on this part. Simple case, case 1, if all numbers are 0, make your answer equals to 0, because that is what you wanted. You wanted that the all numbers turn out to be 0, and that is what you already have. So do you need to perform anything? No, answer remains 0. So this covers our 0 case. That is one of the answers ticked off. I know 0 is a possible answer when all numbers are already 0. So maybe I can keep a simple check over here with some counter variable and simply to check whether all numbers are initially 0. If I do find that, good, great to go, and I'll be simply printing 0 as my answer. Now, if I look at the sample cases, answers are also 1, answers are also 2. So it kind of gives me an intuition that I can maybe create some solution. When do I think the answer is 1 and when do I think the answer is 2, and so on, so on, so on. And can I limit myself to keep the answer to 2? And let's start off with the very first case, that is when do I think the answer is 1? So typically when I say the answer is 1, it means that just doing one operation, you will receive all the numbers to be 0. Now try to imagine this. You have numbers A1, A2, A3, A4, A5, A6 on till n. Now if I'm arguing that only after one operation you gather an answer as 0, as in you gather all the numbers to be 0, that means the collection that you target, the number, or you can say the range of numbers that you target, is so ideal that as soon as you target them, first of all, their max is 0. And that's the only collection you need to target, because after that everything is 0. I'll repeat the whole idea again. If I'm arguing that the answer is 1, there of course has to be only one collection of numbers, some collection of numbers, only one in nature, some yellow margin, where I am trying to do my operation. Of course, these collection of numbers must have the max as 0, because once I do that, all the numbers in this range will become 0. And besides that, every other number in the array has to be 0. This is true. If this is not true, answer cannot be 1. Because you know after one operation you have to stop. You cannot do anything more. I'm limiting myself to one operation only. So arguably this stands. This is a simple common sense. To understand this even further, we can now have a general idea in our head that there is some segment, or not specifically some, you can say there is one segment only filled with greater than 0 numbers in the whole array. So for our idea with operation 1 to run, this has to be true. In the whole array, there has to be exactly one segment which is filled with numbers greater than 0, and you choose that segment and voila, you're good to go. Every number in the array turns out to be 0. Now why is this true? Let's take a very simple example. Let's say you have numbers like 0, 0, 0, then some positive numbers 5, 4, 1, 6, 7, then some 0. Now imagine over here, what's that single segment that is filled with all zeros? All numbers that are greater than 0? This. Select this. Now, it's a very commonsensical point to note out that numbers or collection of numbers which have all numbers greater than 0 will of course have max equal to 0, because the lowest non-negative number that is not present in this collection is 0 itself. So if the max of this is 0 and I select this numbers, this becomes 0. All of these 5 numbers become 0. And arguably I had said that this is the only collection of numbers which is falling in the segment which have numbers greater than equal to 0, greater than 0, and all rest numbers are zeros. So you can see, yes, all other numbers are already 0, and these 5 numbers were initially greater than 0, now they turned out to be 0. So can I say after only one operation, I have turned my array filled with full zeros? Yes. And this is the case when you have only one operation to be executed. I hope this case should be clear. Now let's jump to the third case, and from this you will understand why am I limiting myself to not go beyond any of these cases. Third case is, I am saying I am only performing 2 operations, not more than that. So again, I am limiting myself to 2 operations. Now based on the same idea in the second case, we argued that we had only one segment, exactly one segment, that had greater than 0 numbers. What's the counter of this? Very simple to understand. There can be more than one segment. Of course, let's take an example. Let's say your numbers will look like this, 0, 0, 0. And let's say something like 5, 6, 7. Then let's say maybe some zeros more, then let's say 1, 2, let's say 0, then let's say 3, 4, then let's say 0. So in this you can see that number of segments which are greater than 0, all numbers greater than 0 are actually more than 1. There are 3 in count over here. So can I say I will only perform one operation? Not possible. Like if you run the whole logic in your mind, you will see that I cannot do this in one operation. But I can actually do this in 2 operations very smartly. What I can do over here is, I can select this chain of numbers over here, or to be very specific, why this chain of numbers, I can even select the whole array. Very well, very smart. I can select the whole array with me. Now the whole array will of course have some max, right? Of course that max is not 0, because I know zeros are present in my collection. This max is not going to be 0. Do I need to bother myself with what the max is? No. Currently no. Why? Because understand this, I have 2 operations available with me. So I'm talking about operation 1. What I'll do is, I'll select the whole array. I'll say, okay, whatever max this comes out to be, let's call that max as m. Every number in this array now becomes m. So I have modified the array and it kind of looks like this. After operation 1 has been performed, you can say operation 1 done. After this, array is m. This is like m, so on, so on, so on. You have m's over here. Done operation 1. You selected the whole array. Now you have one more operation in hand. And the argument is, let's use this even more cleverly. How about now I select the array once again, the full array once again. What's the max of the whole array now? The array is filled with a single number that's greater than 0. Of course, this number m has to be greater than 0. M is greater than 0. I know, because when I initially found out the m as max of the initial array, that was not 0. Because 0 was already present. I knew that for fact. So this max has not to be 0. This is some number greater than 0. Like maybe some number greater than 0. 5, 6, 7, 10. I don't care with that part, what number that is. I know it's not 0. So this number m is not 0. It's greater than 0. That means right now I have the array filled with numbers that is a single number greater than 0. If I find the max of this, very simple, no argument, the max of this will be 0. Now the max of this will be 0. Like max of this will be 0. Now if you have performed operation number 2 on the whole array and you are arguing that the max is all 0, then will your array not look like zeros to the very end? Yes, that's true. And this is all that I can argue, because this is where we can stop. Now the argument is, do you require 3 operations? Do you require 4 operations? Do you require more operations? No, because case 1 was when we felt, okay, everything is already 0, report a 0 as your answer, no operations needed. Case 2 was only one segment existed that had all numbers greater than 0. So you said, okay, very smart, rest all numbers are 0. There's only one segment there. Just select that segment, and in that segment, do the operation. Their max will turn out to be 0. I'll be good to go. And that happens. And I showed this operation over here. All great. But what about the third case? The counter to the second case was only a single case where I felt What about I take more segments? That is, I am not limiting myself to be exactly one segment. I have more segments which are filled with numbers greater than 0. And that is the only case will be covered that in the third case. We covered all such possible arrays that could be there in the third case itself. So every other case that falls in the third case can be covered by simply 2 operations, and you will never bother yourself with more operations. And this is why I started off with the argument that you need at most 2 answers to be reported. Either it's 0, either it's 1, either it's 2. I hope this is clear. Pause the video, give it some thought, draw up a lot of cases. Like draw at least 10 cases with your pen and copy, and see that you can find every answer is either 0, 1 or 2. And this is why this problem has such a clever solution. Alright. Now to implement this problem is where things can get a bit tricky, because I need some decent amount of checks to actually figure out when is the answer 0, when is the answer 1 and when is the answer 2. So I'll discuss this briefly over here in pseudo part, and then you'll see the code. For case number 1, you need a very simple check. Maybe I can take a counter. Again, this is implementation difference. Maybe you can come up with much more smarter implementation on your own. That would be good to go. But then I am just showing you my part of code piece where I think this could have been the best thing to implement this out. I am taking a counter variable where I can simply count what is the number of zeros with me in this array. Now, if I feel that the number of zeros in this array is actually the size of the array, then I know that I have all zeros in this array. Great, I'll print the answer as 0. Good to go. Not bothering myself. Case 1 is done. Now, case 2 can be pretty tricky. Why? Because like in this, I have to figure out some check by which I can figure out that, yeah, okay, there is only one segment which is filled with greater than 0 numbers. And that's the only segment that's coming in the array. So how do I do that? In my implementation, what I've used is pointers. What I can do is I can find the very left side of the array where I feel I have found a number that is greater than 0. And I can similarly find the very right hand side of the array where I feel I have found a number greater than 0. So what will that help me do? That will eliminate all the numbers in the start which were zeros and all the numbers in the back which were also zeros, right? So, and so. So I'll finally figure out that I'm standing at a boundary. This is the left boundary. You can say this part is the L boundary and this is the R boundary or left and right boundary. Now in this left to right boundary, what do I finally want to see? In this boundary, there should be no 0, right? If there is some 0, then I know this is case 3, because in case 3, I knew that the left boundary would have been at this location. From the left, this is the boundary where you find the first positive integer or greater than 0 integer. And from here, this is the right boundary, right? So in this segment, you can of course find zeros. That means there are more than one segment inside this boundary. But if I don't find any number in this boundary as 0, then I know this is a single segment which has numbers greater than 0. So if I find no zeros in this boundary, this is case number 2. Hence, I can, with that sort of maybe I can keep some Boolean check. I can see that the answer is true, and I'll say answer reports finally as 1 because I would only require one operation. But if I find that to be false, that is I have found some zeros in this boundary, then I know there are existentially more than one segments of positive integers. I know I will have to take the other route of case number 3. That would mean answer is effectively 2. So this is the whole question. Let's see the code part and see how am I doing this. So I'll take n as input, of course, initially t, then while t loop, then of course n input, and then the r input. So up till here pretty much simple, just taking inputs. Now I have a count of 0 variable, starts at 0. Then I run a loop and I simply say if ai is 0, increment my counter. And then what do I want to do? This up till here, I am doing some things for case check 1. Then after that, I am finding out my code for case 2 and 3. So I am keeping a Boolean variable that is found 0. That is basically the variable that will tell me, did I find some 0 in the left to right range? Starts with false. I have the left pointer at 0 and the right pointer at n-1. Then I run a while loop. I say till a of left is 0, increment your left. So you can imagine this, that if you go back to the diagram, you can say, okay, left starts from this location and I keep on incrementing it till I stop at a location where I feel I have found a positive integer. Same thing is done in the right hand side. So I'll say, okay, while a of left is 0, increment your left. While a of right is 0, decrement your right. Now you have, of course, arrived at left and right boundaries where I know I have the first left positive and the rightmost positive integer found out at those pointers left and right. So I can run a loop in that range, left to right. I is equal to left, I is less than equal to right. If I find the number in this range to be 0, I know I have found a 0 in this segment. And this is where I finally end all the checks possible for 1, 2 and 3 case. Now I'll write simple if and else checks. If case number 1, this is, you can say case 1. If I feel that count of 0 is equal to n, that means initially all the array is 0. So no problem, simply print 0, that's the number of operations you perform, that is nothing. If you feel that you are in else if case where found 0 is false, which means you did find a boundary, but in that boundary you never found any 0. So that means there is only one segment, hence answer is 1. And else you go in the else part, this is case 3, and this is where you have found the whole solution to the problem. Now what of the time complexity? I'm of course running an n loop over here, so this is n order. This is also n order. And then you can imagine that I'm running a while pointer over here. So while pointer of course runs some iterations from the left. So maximum this can be n order, right? Like I'm just taking a very brute solution. Like of course this is not going to be n order. This is going to stop somewhere, like maybe like first 10, 15, 20 numbers is going to explore, and then it stops at some location where you have found a positive integer. But to be reportedly in terms of n, it should be in n order, because what can happen is maybe you explore all the numbers possible, just dropping out the last number. So maybe you stop at somewhere in the half range of the limit. So it's kind of that n by 2 order, which is effectively n order. And similarly is the problem for this. So this is, can also be reported in n order. And then this loop also is somewhat in n order, because what if you don't explore left and right a lot, and the middle range which you actually have to explore is very, very big. It's kind of in an n order range again. So it's n order again, which means effectively whatever happens, I am worst case traversing an n order complexity. Now this is very, very good for me, because this means I am effectively getting 2 into 10 raised to 5 solution, right? 2 into 10 raised to 5 order solution. And this is of course going to work, because I wanted a solution that was in 2 into 10 raised to 8 number of solutions, operations. So logic being right, this fetches me an accepted solution. And what of the space complexity? Space is also O of n, which is 2 into 10 raised to 5 order only, because I know that the net space I consume over the test would be in 2 into 10 raised to 5 order. That is all the summations of n I declare in all the vectors. So that is the whole solution to the problem. So definitely a very clever problem, right? This 0, 1, 2 case making was very important. This intuition comes from the fact that if you observe the cases, you can also see the answers are only rotating to 0, 1, 2, 1. So it kind of hints you in the direction also that, okay, the answers are maybe not looking greater than 2. And then once your mind starts thinking towards this ideology that how do I prove myself wrong, then the answers don't cross 2, you will actually make these cases on your own, and you will understand that yes, I am exploring all the possible arrays and I'm never crossing 2 operations. Hence this solution. Alright, so I hope you like the video. Thank you for watching.